test for divergence. Let's learn about the test for divergence, sometimes called the nth term test. Given a series, the sum of n equals k to infinity of a sub n, if the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. If the limit as n approaches infinity of a sub n does equal 0, then the test is inconclusive. Informally, what this says is that if the terms are not heading to 0, then the series must diverge, because there's no way this infinite sum can be a finite number if the terms themselves that we're adding on aren't heading to 0. If the terms are heading to 0, that's not enough to determine if the infinite sum happens to be a finite number. Okay, let's jump into some examples where we apply this test for divergence. For the following series, determine if they diverge by the test for divergence, or the nth term test, or if the test is inconclusive. Now, we're going to learn a lot of tests in this series unit, and this truly is the first one that we would generally apply. What it involves is finding the limit as n approaches infinity of the general term. So e to the n over n. E to the n is an exponential. It's growing bigger faster than n. So if we use the laws of dominance, we know that this is infinity. And that is not 0. So these terms are in fact getting bigger and bigger and bigger. So there's no way that it could add to a finite number. So by the test for divergence, the series diverges. So we would say this series diverges by the nth term test, or you can put test for divergence, and then because the limit as n approaches infinity of e to the n, make sure that's in the exponent, e to the n over n, is not 0. In this example, we have the sum of n equals 1 to infinity of 2n plus 1 over 3n plus 2. So we take the limit as n approaches infinity of 2n plus 1 over 3n plus 2, and we can recognize that the numerator and denominator have the same degree. So towards infinity, we can say that the answer is just their coefficients, so 2/3. And 2/3 is not 0. So because the limit as n approaches infinity is not 0, that means that this series diverges by, this time I'll call it the test for divergence, because the limit as n approaches infinity of 2n plus 1 over 3n plus 2 equals 2/3, which is not 0. Now, before going any further, I'm sure you're thinking, do I have to write all of this out? And the answer is yes. In this section, it is important that we justify that we have met the hypothesis of the test that we're using, that we name our conclusion, what test we used, and how we satisfied the hypothesis in order to reach our conclusion. For this example, I have the sum of n equals 1 to infinity of 1 over the square root of n. So if I do the limit as n approaches infinity of 1 over the square root of n, I have a constant over a function of n that's getting bigger, so this entire fraction is going to 0. Now, what does that tell me? Nothing. The test for divergence is inconclusive. So this infinite series, it could converge, it could diverge, we don't know. So we would have to apply another test eventually when we learn additional tests. But for now, we would say the nth term test is inconclusive. And we can see our work that the limit was equal to 0, and that's why it's inconclusive. So the terms are getting smaller and getting closer to 0, but that's not enough to determine that this converges, and if this was anything other than 0, then we would know it diverges, but equal 0 is inconclusive. On this example, I have the sum of n equals 1 to infinity of negative 1 to the n times the square root of n. So let's write out the limit as n approaches infinity of the quantity negative 1 to the n times the square root of n. So let's take a moment to think about this graphically, just to help us understand this limit. If we ignore the negative 1 to the n and we just think about the square root of n, we're going to observe that the square root of n is just getting bigger and bigger and bigger as I plug in numbers towards infinity. The negative 1 to the n is going to make those outputs alternate in sign. So if I substitute 1 in first, negative 1 to the 1 is going to be negative. So every other value is going to be negative. And so my outputs are getting actually further and further away from 0, right? They're bouncing back and forth. They're not getting close to any particular number. So this limit does not exist. So we can say our series diverges by the nth term test because the limit is not 0. For this example, I have the sum of n equals 2 to infinity of n over the quantity natural log n cubed. Just a small observation here that the starting index is 2 because if I substitute in 1, natural log of 1 is 0, and I can't start with an undefined quantity. So our starting index is 2, but that doesn't really matter in terms of the test for divergence because we want to see what's happening as n approaches infinity. So if we set up the limit as n approaches infinity of n over the quantity natural log of n cubed. Now here, this is kind of an interesting one because I have a polynomial on the top. And on the bottom, I have a composition. I have a natural log function, which normally we think, okay, grows slower than the polynomial on top, but natural log n is being cubed. So it's not really clear cut which one's growing bigger faster. I don't have just a polynomial over just a logarithm. I have a logarithm inside of a polynomial function, a composition. So here I have this infinity over infinity case in general, so I can apply L'Hopital's rule. So if I apply L'Hopital's rule, I tend to write a little LH over the equal sign so I remember what's happening here. I am taking the derivative of the numerator and denominator separately. So the derivative of n is 1. This is going to require the chain rule. So I'll have 3 times natural log n squared times 1 over n times the derivative of the inside. So that's the derivative of the bottom using the chain rule. So what I have going on here now, I'm not doing L'Hopital again, I'm just simplifying. I'm going to multiply the top and bottom by n to clear out that 1 over n. So if I multiply the top and bottom by n here, I'm going to have n over 3 natural log n squared. So again, I am at an still unclear result. So I have a polynomial on top, n to the first, and again, natural log, but inside of a function squared. So I don't know which one's getting bigger faster here. So we're going to do L'Hopital's rule again. I'm going to work horizontally here. So we have the limit as n approaches infinity. The derivative on top is 1. Another chain rule is going to give me a 6 times natural log n to the first times 1 over n. Let's clear that n again. And so we end up with the limit as n approaches infinity of n over 6 natural log n. And now we're getting somewhere. So now I have just a polynomial n to the first over a logarithm. So that polynomial on top is getting bigger faster. So this whole thing is going to infinity. So since that's not 0, we can draw our conclusion. We can say the infinite series diverges by the test for divergence because the limit as n approaches infinity is not 0. On this one, I have the sum of n equals 1 to infinity of e to the n squared over n factorial. If I set up the limit as n approaches infinity of e to the n squared over n factorial, I'm actually going to get stuck because I have this infinity over infinity case that the laws of dominance are, again, not going to help me with. So I have a factorial on the bottom, yes, but on the top, I don't just have an exponential. I have a polynomial n squared inside of an exponential. So how do I know which one's bigger, right? The polynomial inside of an exponential, that could be growing faster than n factorial. I'm not sure. So I have infinity over infinity. I would think maybe to try L'Hopital's rule, except we don't have a differentiation rule for factorials. So here we cannot apply L'Hopital's rule, and we can't determine the limit, right? So we can't find the limit. So in this case, we can't even apply the test for divergence. So we didn't meet the requirements. We can't find the limit as n approaches infinity, so the test for divergence doesn't apply. Now, eventually, as I mentioned, we are going to learn other tests, ones that are going to really help us when factorials are involved. But on this particular example, I can't find this limit at infinity, so I can't even apply the test for divergence. So now to sort of wrap up, we're going to just reiterate a common mistake. So the warning here is that if the limit as n approaches infinity of a sub n does equal 0, that does not mean that the infinite series converges. So the nth term test, or this test for divergence, is a failure test only. So it can only show divergence. And the most classic counterexample is looking at the sum of n equals 1 to infinity of 1 over n, because that is a divergent series. So 1 over n as a series diverges, even though when you look at the limit as n approaches infinity of 1 over n, that does equal 0. So remember what we said, it's not enough for the limit of the general term to equal 0. The series could still diverge, and here's an example of that. And we're going to show next one way to show that the sum of 1 over n diverges. Let's take a close look at this harmonic series. The harmonic series is the sum of n equals 1 to infinity of 1 over n. It has a name, and it diverges. It very famously diverges. And we're going to show one way. There's a lot of ways to show it diverges, but I'm going to go through one way we can show it diverges, that it is not a finite number when you add them all together. So the sum of n equals 1 to infinity of 1 over n, if you write out a bunch of terms, it would be 1 over 1 plus 1 over 2 plus 1 over 3, 1 over 4, all the way to 1 over 8, and so on, right? I'm just stopping at 1 over 8. I think that'll be enough to convince us here. So we want to convince ourselves that this list of numbers here is greater than or equal to this second list of numbers here. Greater than or equal to. Well, 1 is equal to 1. 1/2 is equal to 1/2. 1/3 is greater than 1/4. I'd rather have a third of a pizza than a fourth of a pizza, right? 1/4 is equal to 1/4. 1/5 is greater than 1/8. Again, we're trying to show this top row is greater than or equal to this bottom row, or the second row. So 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8. And 1/8 is equal to 1/8. So hopefully you're convinced that this top expansion is greater than or equal to this second expansion here. And then now let's do some groupings of this row right here. So this row, this sum right here, is equal to, now, well, 1 is equal to 1, 1/2 is equal to 1/2. These two terms, 1/4 plus 1/4 is 1/2. And then these next four terms here, 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4/8. That's another 1/2. So hopefully we can sort of convince ourselves that we could do the same thing if I keep going out. If I have 1/16 and I have 8 copies of that, then that's another 1/2. And so 1 plus a half plus a half plus a half, if I keep adding a half, that number is just getting bigger and bigger and bigger, and that's going to infinity. Okay, well, we just said that the sum of n equals 1 to infinity of 1 over n is greater than infinity, right? So the harmonic series diverges, even though if I look at that list of numbers, it is going to 0. It is getting smaller, but that's not enough because this infinite sum is bigger than infinity, right? So it doesn't converge to a finite number. Let's do a main idea summary or a recap. So let's say we're given an infinite series, the sum of n equals 1 to infinity of a sub n. If we can find a partial sum formula, s sub n, then we can evaluate the limit as n approaches infinity of s sub n, and the infinite sum is equal to that limit. But it can be difficult or impossible to find a partial sum formula s sub n. One that you can find is telescoping, but definitely not all series are telescoping. Very rarely are they. If the limit as n approaches infinity of a sub n is not 0, if the terms are not headed to 0, then the infinite series must diverge. This is the test for divergence, or the nth term tests. So if the limit of the general term is anything other than 0, if it's not 0, then the series diverges. But if the limit of the general term is 0, the test for divergence is inconclusive. The series might converge, but we don't know yet, right? We need more tests. So if the limit as n approaches infinity of the general term equals 0, the series could converge, but like the harmonic series, it could diverge. So we just don't know. The test for divergence, though, is inconclusive.